Okay, let's talk about asynchronous backtracking algorithm. So this is another way of finding a solution to a constraint satisfaction problem. So I'm gonna put a little example here. We're gonna be using graph coloring as our example. So here we have just three nodes, x1, x2, and x3. And let's say, this guy could be either white or blue. White or blue, and let's say this one is just could only be blue. So the idea behind asynchronous backtracking is that each one of these is an agent, right? They're going to be working in parallel, and each agent sets himself to a color, right? So X1 knows he can be either white or blue, so he just goes ahead and sets himself to a color, right? So each agent I kind of starts out by just sets himself to a color, sets himself to a color, to some color, and then asks the agent I tells others or asks others, is this okay? So basically, this is one of the messages that gets sent. The agent says, is it okay if I, I or xi, I'm white? Is that okay? And similarly, of course, the agent is going to get these okay messages from all his neighbors. So he asks his neighbors, by the way, not everybody. The neighbors are the ones you share a constraint with. So you ask your neighbors, is that okay? Similarly, of course, at the same time, you're getting all these messages from your neighbors. Okay, is this okay? Is this okay? So all those okay messages that you get from your neighbor plus your caller, you put those in a variable we call the local view. So that again is just it's just a table of the color that you think everyone is at this time. And some of them you might not know, right? So maybe I know that this guy is white and this guy is blue, but I don't know about it. This guy, X3. So my local view is just my current table with what I know about everybody's current color. Remember, this is all asynchronous, so this could be, not exactly true at this time, but nonetheless, it's the best I got. So there you go. So I send everybody I build my local view based on everybody's okay messages. And then when I have this local view, when this local view is updated, I check. So this is, I check to make sure that, my caller, say I'm X1, I make sure that my caller works with everybody else's callers, right? If it works, then I'm okay. I don't do anything. So once I get the local view, I'm going to check. So basically, I check for constraint violations, mostly involving my caller. Violations, and then more specifically, determine determine if there's a caller I can set myself to if there is a caller for me. For me, that does not violate any constraints. So I'll just say that works. But that's what it means to work. So I say if there's a color for me that works, then I set myself, and if that color is, by the way, different from the one I'm already at, then I basically I set myself to it. We repeat the whole thing. So I set myself to another color, and then I tell my neighbors, is this okay? And then everybody gets those views. That's part of the local view. Everybody checks, determine if there's a constraint violation. If there is, if there is, and I can find a color, then I change that color. I go up here. Now, you get into trouble in a couple places. Maybe there is no color for me, right? So determine if there's a color for me that works, and if so, we go back up here. But there's this else part here. I'm gonna have to shift this up here a little bit. So this is if there's a color, else there's no color for me. that works. And so what I do that is I generate a no good, right? Using the hyper resolution rule, or really anything. So I generate no good. Like basically, I look at my local view. I say, it's no good. What I see here is no good. Right? It's no good if x1 is white and x2 is blue. So usually again we'll use the hyper resolution rule. We'll say something like this: it's not good if x1 is white and x2 is blue. Maybe there's some other stuff. And then I take that no good. I'm gonna go over here, and I send that no good to the lowest priority neighbor agent in that no good. So there's no good here involves x1, x2, and let's say only x3. So the lower priority that there is, we assume there's some priority set. Let's say the 1 is the highest priority and 3 is the lowest priority. So there's some priority ordering of the agents. So the one with the lowest priority in that no good, in this case, our friend right here, 3. Oops. Right there. 3 is the lowest priority. So he's going to be the one that gets that no good, right? And so what happens then when 3 gets a no good, or any agent gets a no good, that no good again gets added to the database of no goods or constraints that every agent has, right? So one thing I neglected to mention is when we start out, each agent has this set of constraints or no goods. It's the same thing. So initially this is just populated with the 2, in this case, the 2 constraints for x1. It could be more, of course, in other examples. And then when you get a new no good, you add that to your own database. So you add that as a no good, and then you send it to the other guy, the lowest priority agent in that no good, and then he adds it to his database. And once he adds it to the database, he again goes through and checks for constraint violation, determine if there's anyone that works for me, etc. Right. So that's the basic idea of backpropagation. If you look at the algorithm itself, here it is from the textbook. You can see it's implemented. Each agent has to handle an OK. So when you get an OK from somebody else, you just add it to your local view, and then you check if that local view works. So if I cannot find a value that is consistent with my local view, I'm going to backtrack. Otherwise, I'm going to change my color, and I'm going to tell everybody about my new color. So I'm going to ask everybody to handle OK. The backtrack is, so if I cannot find a value consistent with my local view, that's when I backtrack. And this is the part right here, line 1, when I find my new no good or no goods. One thing I forgot is this line. If there is an empty set of no goods, basically I derive a contradiction. So at that point, I know there is no solution. So we can terminate the algorithm. If I do find some no goods, then I can select one. I can select the agent with the lowest priority, and I tell them to handle that new no good. And that's this function here. Then, of course, I add it to my local view. I'm sorry, I removed that agent's color from my local view because it's no good anymore. He's going to change it soon anyway. So when you get a no good here in line 1, this is when we add it to the database. So record a no good as a new constraint. So that's a new constraint. The other thing we had to do is that now, because this no good could include agents that were not my neighbors before, I have to figure out, just find any agents in that no good that were not my neighbors and add them to my list of neighbors. And then I change my value and I check my local view again and see if that needed changing. If it didn't change, which I usually would, I send everybody a handle OK. So that's all the algorithm. Now, the 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 thing about this is, so a couple of things about when you run this algorithm in the real world. So ABT, or synchronous backtracking, what happens is, the no goods get sent to the lowest priority agent. No goods, go to the lowest priority. So what ends up happening when you run the algorithm, you implement it, you look at it, is that you get something like this. The number of messages that are processed, and let's say this is the x-axis is the agent. So put the agents on the x-axis, and the lower priority agent is here. Lower and higher priority agent, and as you might expect, is the curve is something like that, where the lower priority agent, like this guy, does a lot of work, and these guys over here, it falls out pretty sharply. The higher priority agents do get no messages, so they do no work, and that is why, because we're sending in no goods to the lowest priority agent. However, we can't just, you say, well, why did that? Why not just send it to somebody randomly? Well, you can't do that because ABT is complete. So it will find a solution if there is one, and it will tell you if there is no solution, if there isn't one. If you get rid of this issue about sending it to the lowest priority agent, you cannot, the proof doesn't work, right? The proof of the completeness proof relies on the fact that we're sending this to the lowest priority agent, so there are no loops. It's hard to prove completeness if there's a possibility that your algorithm can get into a loop, right? So an agent sends a message to another one, sends it back to this guy, the other guy, and then back to here, and then these guys just keep flip-flopping their colors, between, say, white and blue, or something like that, which happens all the time. You get into those kind of flip-flop, everybody changing colors, and so that's what would happen if you got rid of sending it to the lowest priority agent without doing something else a bit more clever. So ABT is complete, but because of that, it is fairly unfair, and so it takes a long time because basically you end up mostly centralized, right? So it's really mostly centralized in practice.